And our next speaker is Shangdong Ro. I hope I pronounce well, which
yes, that's
will
correct.
tell us about studying high mass microquasar with HAWC. I give you 3 minutes before the end of time.
Okay, thank you. Can you see my slides well?
Perfectly, yes.
Okay, that's perfect. Okay, hello, my name is Changdong Ro, as introduced, and I'm a postdoc at the University of Seoul. And I've been working as a member of the High Altitude Water Cherenkov Observatory since I was a graduate student studying gamma ray binary systems from the Northern Hemisphere with tera electron volt gamma ray data. And today I plan to show you about our work on some of the high mass microquasars, which has recently been published through the APJ letter. So after the talk, if you would like to find out more, you can obviously ask me questions, but also please feel free to look up our paper on the archive. Okay, so in this work, we studied 4 high mass microquasars, namely LS5039, SIGX1, SIGX3, and SS433, which are microquasars within the field of view of HAWC. And for the purpose of our analysis, we assumed that these high mass microquasars may have some common multi-wavelength emission mechanisms that could be used to study them as a single type of very high energy gamma ray source. And we did this by applying a stacked analysis. But also we did some individual studies on each of the sources to place upper limits at the energies that have not been looked at thus far. Also, the table on this slide shows some of the general properties of the 4 microquasars that we used during the analysis, but these are not what we found, so I won't go through the table explicitly. All right, so before I show you the results, the High Altitude Water Cherenkov Observatory, or HAWC, is located at a latitude of 90 degrees north at an altitude of 4.1 kilometers near Sierra Negra, which is a volcano in Puebla, Mexico. It has 300 water Cherenkov detectors, so 300 of these water tanks. These are very large. They don't look so here, but they're about 5 meters tall. And so together, they create a combined geometrical area of approximately 22,000 square meters. So HAWC is well suited for studying multiple microquasars simultaneously because we have a wide 2-steradian field of view and also very high, over 95% duty cycle. And we don't need to focus on any of the sources. So that's the advantage. Also, our official energy range is between 300 GeV and 100 TeV. So we are really at that high energy end of the spectrum, which allows us to study how energetic these microquasars could be. Okay, so for the analysis, we used 1523 days of cumulative HAWC data, where we fitted for the flux normalization of each of the 4 sources, assuming a point source morphology with a simple power law spectral model. As briefly mentioned before already, we applied 2 main techniques to study the 4 high mass microquasars, where the first one is computing the flux upper limits for the 4 quasi-differential energy bins with the spectral index fixed at -2.7. The second technique is the stacked analysis, for each of which the sources are fitted at 7 TeV while scanning through the spectral index between -2.0 and -3.0. Okay, so in the next 2 slides, I have the results for the first technique, i.e. the spectral energy distributions of each high mass microquasar, ranging from 100 EV to 100 TeV. In these plots, the blue are the data points or upper limits from other experiments. Also for each plot, the gray band shows the emission region that is likely to be dominated by the thermal emission of the accretion disk. The left and right vertical gray dashed lines for each of these plots correspond to the break in the synchrotron and inverse Compton spectrum, respectively. As for the HAWC results, the red arrows on the far right are the 95% credible intervals for the 4 quasi-differential energy bins, and the yellow and green bands are the HAWC expected limits for the background-only data. All right, so for SIG-X1 on the left panel, you can see that the Hawk upper limits are consistent with the expected limits, and they're also consistent with the general trend of the data points ranging from X-rays to MEV and GeV gamma rays from other experiments. As for SIG-X3 on the right, again, the Hawk upper limits are consistent with the expected limits. And when compared to the gamma ray upper limits from Veritas, I believe, the Hawk upper limits are actually more constraining at above 5 TeV-ish. On the next slide, I have the SED for LS5039 on the left, where the Hawk upper limits are slightly higher than the HES data points, because HES actually confirmed that LS5039 is a TeV gamma ray source, one of a few very high energy gamma ray binaries, in fact. But with Hawk data, we do not yet see significant emission from the source. Lastly, we have SS433 on the right, where the Hawk limits once again seem to be consistent with the upper limits from other imaging Cherenkov telescopes. Next, I would like to talk about the second technique, i.e. the stacked analysis. So this analysis relies on the stacked likelihoods of many independent fits of numerous sources, comparing the same physics model to the data of multiple sources, rather than comparing with each other the sources that we are studying. In a stacked analysis involving multiple sources, the choice of a contribution factor is very important, as it is the contribution factor that decides how the fit to each source contributes to the total likelihood. Therefore, this technique is model dependent. All right, so in our work, we tested two different scenarios or physics models to classify the 4 high mass microquasars. For scenario 1, we assume the gamma ray luminosity of the high mass microquasars is proportional to the kinetic power of the jets, which is a more general assumption that may be satisfied by various gamma ray production mechanisms, including hadronic processes like the neutral pion decay. On the other hand, for scenario 2, we assume the gamma rays are produced when relativistic electrons accelerated by the jets upscatter the optical photons from the companion star. So this one would be exclusively leptonic. So now I will try to explain a little more in detail the scenarios 1 and 2. So as I've said, scenario 1 assumes the gamma ray luminosity is proportional to the jet power, where the gamma ray flux is given by the second equation on this slide. Hence, for the stacked analysis, we used the jet kinetic power over the distance squared as our contribution factor. Afterwards, we used the obtained gamma ray upper limit to compute the 95% credible interval on the jet emission efficiency above 1 TeV, which was found to be 5.4 times 10 to the minus 6, which is approximately, I believe, 3 to 5 orders of magnitude lower than the emission efficiency in X-rays. Also, our best fit spectral index for scenario 1 was 2.2. Next, we have scenario 2, where we are now using the relation between the inverse Compton and synchrotron fluxes as given by the first formula. So this model assumes the particles are powered by the magnetic fields of the microquasars. Okay, so similar to the first scenario, we model our gamma ray flux formula for scenario 2, which is given by this equation. Where in this case, our contribution factor is now the product of the synchrotron flux, the energy density of the radiation field from the companion star, and the Klein-Nishina factor.
3 minutes.
Okay, thank you. And once again, we can use the obtained gamma ray flux upper limit and this equation to compute a lower limit on the magnetic field strength of the high mass microquasars, which gave us 22 Gauss with the ratio of the observed X-ray and MEV gamma ray flux due to synchrotron emission at 10%. This 22 Gauss is consistent with the 20 Gauss field obtained for LS5039 in a 2015 paper, which used a relativistic hydrodynamics model. Therefore, the strong B field found by our stacking analysis suggests that the X-ray to MEV gamma ray flux is not dominated by the synchrotron radiation of the very high energy electrons. Okay, so in summary, no significant EV gamma ray emissions were detected from the 4 high mass microquasars in the field of view of HAWC, but we have placed the most stringent limits for energies greater than 10 TeV, as far as I know. And for the stacking analysis, specifically for scenario 1, we've derived an upper limit on the gamma ray emission efficiency above 1 TeV, which also constrains the high energy neutrino emission efficiency, implying that neutrino detection is going to be challenging for existing neutrino detectors. Also, our results from the second scenario constrains the contribution of synchrotron emission by relativistic electrons as the dominant mechanism between 10 keV and 10 MeV for the 4 high mass microquasars. And finally, we've also studied the HAWC daily light curves for each of the 4 microquasars, which I don't have the time to show you today, but using the Lohm-Scalver periodograms, no orbital modulations in their fluxes were observed at this time. Yeah, thank you for listening.
Thank you. Do we have any question? I see Asaf has a question.
Yeah, thank you for a very nice talk. So just a clarification, you said that the lower limit of 22 Gauss, at what radius from the jet core is that?
What radius of from the jet core?
Yeah.
So the HAWC PSF is much larger than what you would think. So it's like half a degree.
Okay.
So we can't really, so we can't really look that specifically and decide how far away it is from.
So it's kind of an average over the entire.
Yes. Yes, exactly. Yes. Yes.
All right.
That's correct. Yeah.
Okay. Thanks.
Do we have a question in the room? We don't hear you.
Yeah, okay. I would like to ask a question actually. Is there a way to improve first the geometrical, how to call that, the resolution, spatial resolution of the observation at this energy? What will be the way? And to decrease the sensitivity also, I mean, to increase the sensitivity of this instrument or this type of instruments?
Yeah, so for HAWC, well, the main point of these particle sampling arrays is to achieve wide field of view and high uptime. So really to achieve better angular resolution, you want to go with the imaging Cherenkov telescopes. So in a way, if we can have a combination of a particle sampling array and an imaging Cherenkov telescope, then we can always scan the whole sky with the particle sampling arrays. And then when we find something interesting, we can point the imaging Cherenkov telescope in that particular location from which you can focus and have much better angular resolution than you would with just a particle sampling array.
Thank you.
Any other question online or in the room? Maybe for curiosity, how long are the stacked observation?
Sorry, how long?
Well, how long did you? What is the exposure, the total exposure of the stacked observations?
Oh, so it's 1523 days of cumulative data, but HAWC doesn't need to focus on a certain part of the sky, so we observe all the stars that we can see all the time.
Yeah, sure. Thank you.
Thanks.
So if we don't see anything on the Slack. So if we don't have another question, we can thank the speaker again.